Okay, so we would like to solve the problems of worksheet C for exam 2. And we start with the first problem where we're given the function f of xy equal to ln of x minus y cubed. And we would like to compute the directional derivative in the direction of the vector 1 over square root of 2, 1 over square root of 2 of f at the point 9, 2, which means that what we want to compute is the dot product of the gradient of the function at the point 9, 2 with the direction vector 1 over square root of 2, 1 over square root of 2, because this is precisely what the directional derivative is given by. So to find the gradient, we find the partial derivatives, 1 over x minus y cubed. F sub x is equal to, at 9, 2 is equal to 1. And f sub y is 1 over x minus y cubed times 3y squared. And f sub y of 9, 2 is going to be 12. So our gradient at the point 9, 2 is equal to 112. And if we take the dot product of 112 with 1 over square root of 2, 1 over square root of 2, then we simply find 13 over square root of 2, which is the directional derivative that we're looking for. Let's go to problem 2 now. So here we have the function f of xy equals to y over x plus y. And we would like to compute the rate of change. So rate of change in the direction of fastest increase. For the point -2, 3. Okay, so what we do is, first of all, let's identify what we're looking for. We really want to find the gradient because that gives us the direction of fastest increase. And it turns out that the rate of change in that direction, which it has to be given by a unit vector, the normalization of the gradient, is going to be the magnitude of that vector of the gradient. So let's begin by computing the gradient. To compute the gradient, we need again to compute the partial derivative. So that will be partial derivative with respect to x is -y over x plus y squared. You can use the quotient rule for this, but what I like to think of here is that when I have the derivative of 1 over g, that's the same thing as minus g over g squared. I'm sorry, minus g prime over g squared. That's according to the chain rule, if you will. And that's what I just used here. And f sub x at -2, 3 is equal to -3. How about f sub y? Let's use the quotient rule here. So we will have 1 times x plus y minus y times 1 over x plus y squared. And this will be x plus y minus y. So this will be x over x plus y squared. And f sub y -2, 3 is going to be simply -2. So what is the gradient? The gradient at -2, 3 is equal to -3, -2. And the magnitude of the gradient, which is really what we're looking for, is square root of -3 squared plus -2 squared, also known as square root of 9 plus 4, or square root of 13, which is our final answer. Okay, let's go to our third problem. So we consider the surface with this equation. And the first part wants us to find a function so that the above surface is a level surface. I mean here, we want to name this function f of x, y, z, and you can get pretty much anything that has x cubed plus y squared plus z squared. I like to also subtract 4 so that it's the level surface corresponding to 0. So this is level surface of f corresponding to 0. The second thing is to find a non-zero vector perpendicular to the given surface, and that's none other than the gradient at a specific point. Sorry about this. Zoom sometimes plays these games. So -1, 1, 2. And here the partial derivative with respect to x is 3x squared, so that makes it 3. With respect to y is 2y, so that gives you 2. And with respect to z, that's 2z, which gives you 4. And the last part is this is going to be perpendicular to our surface, normal to the tangent plane. So since you know the normal vector and the point, you can find the equation of the plane, which will end up being a tangent plane, the tangent plane. 3 times x plus 1 plus 2 times y minus 1 plus 4 times z minus 2 is equal to 0. Again, here I remind you that the part of the theory that we're using is that if you have a plane that has a known point on it and a vector perpendicular to it, also known, then the equation or an equation for the plane is given by this formula. And don't forget to set it equal to 0, because otherwise you don't have an equation. Okay, so this is simply a reminder. Let's go to problem 4 now, where we want to find and classify the critical points of the function f of xy equals to x cubed plus 3xy plus y cubed. So find and classify the critical points of f. So we need to find its derivatives. And set them equal to 0. And here, if you divide everything by 3, you will have x squared plus y is equal to 0, and x plus y squared is equal to 0. Solve the second equation with respect to x. You will have x is equal to -y squared, and plug it into the first equation. That will give you -y squared plus y is equal to 0. Y to the fourth plus y is equal to 0. Let's factorize this as much as we can. Y times y cubed plus 1 is equal to 0. This has an obvious root, which is -1. And a very simple synthetic division is going to give us y squared minus y plus 1, which is a second-degree polynomial, a quadratic polynomial, if you will, that has negative determinant, discriminant, and has no roots, no real roots. So the only possibilities are y equals 1 and y equals -1. Well, if y is equal to 1, then this equation tells us, y is 0 and y is equal to -1. If y is 0, then the first equation tells us that x is 0, which means we have the point 0, 0. And if y is -1, then the first equation tells us that x is equal to -1, which means that we have the point -1, -1. Okay, so let's find the second order partial derivatives in order to apply the second derivative test. And fyy, which is 6y. So at 0, 0, d is going to be fxx at 0, 0, fxy at 0, 0, fxy at 0, 0, and fyy at 0, 0, which is going to be 0, 0, 3, and 3. That's a -9. That's a saddle point. Okay, I also like to call these Pringle points. You have the same kind of shape following Terence Tao, who, from whom from a video of his or a blog of his, I saw this nice identification of another object that has the required shape. And for the second critical point, what do we get? We get a -6 here, a -6 here, a 3, and a 3, which gives us 36 minus 9, also known as 27, which is greater than 0. That means that there is a local extremum, and if we sample one direction, the x direction, for example, we see that this is negative, which means that's the shape of a frown. That's a local maximum. So we found one saddle point and a local maximum. Okay, let's do problem 5, Lagrange multipliers. So we want to find the minimum and maximum of f of xy equals x plus y on the ellipse x squared plus 2y squared equals 6. So again, let's define a function that has the constraint as a level curve. So g of xy equals x squared plus 2y squared minus 6. And then the method of Lagrange multipliers tells us that at critical points on this ellipse, we will have that the gradient of the objective function, meaning of f, is parallel to the gradient of g. And of course, g should be 0 just to make sure that we don't leave our constraint. So the gradient of f is very, very simple, 1 and 1. And the gradient of g is 2x and 4y. And of course, x squared plus 2y squared has to be equal to 6. And we get that one is 2 lambda x, and one is 4 lambda y, and x squared plus 2y squared is equal to 6. How do we solve this? Well, start with the observation that x, y, and lambda cannot be 0. Yeah, I mean, if you have them as factors in a product that is equal to 1, there's no way that they're 0, which means that you can divide the first two equations, and that will make things very, very simple, right? It will tell us that 2y is equal to x. And once you know that 2y is equal to x, then you can plug it into your constraint. So you will get 2y squared plus 2y squared is equal to 6. And that would give you 4y squared plus 2y squared is equal to 6. 6y squared is equal to 6. Y squared is equal to 1. Y is equal to plus or minus 1. And since x is 2y, if y is 1, you will get that x is 2. And if y is equal to negative 1, then x is negative 2. So we got the points 2, 1, and negative 2, negative 1. Our function is guaranteed to have a minimum and a maximum because it's defined on a compact set, namely the ellipse. So if we evaluate the function at the two only candidates for for extrema, not just local, global extrema that we found, then that should give us the minimum and the maximum. So evaluate it at 2, 1, you will get 3. Evaluate it at negative 2, negative 1, that will give you negative 3. This is the maximum, and this is the minimum. And that completes this problem. Let's go to our integration problems now. The first one that we have is a double integral, which can very easily be written as an iterated integral. So 0, 2, that matches with dx, 0, 1, that matches with dy. And we have x plus y squared. So this is going to be x squared over 2 plus y squared x from 0 to 2, integral from 0 to 1 dy. And this will be 2 plus 2y squared, integral from 0 to 1 dy. And this will give you 2y plus 2/3 y squared from 0 to 1, which is 2 plus 2/3, also known as 8/3. And that's it. Okay, 2 more problems. Problem 7 is we start with the integral from 0 to 1, y to 1, e to the x squared dx dy. We realize that we cannot find an antiderivative for e to the x squared. It exists, but it's not expressible using functions that we already know. Hence, what we do is we try to ask ourselves, what if this double iterated integral came from a double integral by the wrong choice of the order of integration? In other words, what if we explore the possibility that we integrate first with respect to y, then with respect to x? Well, to do that, we should know what the domain of integration was. And here, since we're integrating horizontally first, that means that we have a left boundary and a right boundary. And the left boundary is x equals y. That's the bisector of the first quadrant. The right boundary is x equals 1. That's a vertical line. The vertical range of all these horizontal integrations is from 0 to 1, which tells us that it's exactly this triangle right here. So if we now want to go dy first and then dx, then we will have a lower boundary, which is the x-axis, also known as y equals 0, and the number boundary, which is again the bisector of the first quadrant, and in terms of y is given, or in terms of x, if you like, y is equal to x. And so these are vertical integrations that we do. The horizontal range of all these vertical integrations is from 0 to 1. So 0 to 1. And our integrand is e to the x squared. And now we're not set. We still have work to do in order to compute it, but things are looking up, at least for the first integration, because we're integrating with respect to y, and this is constant. It doesn't have a y in it, so its antiderivative will be y e to the x squared, and this is going to be from 0 to x, 0 to 1 dx. So this will be simply x e to the x squared integral from 0 to 1 dx, which we shouldn't have too much trouble finding this. We can try substitution. U is equal to x squared. Du is 2x dx. And x dx is 1/2 du. So this will be 1/2 times the integral of e to the u du. Remember, when you have a substitution, you want to apply the substitution to the endpoints. So this will give you from 0 squared to 1 squared, which is, of course, from 0 to 1. The antiderivative is e to the u. I just put 0 squared and 1 squared so that we don't forget that this is, that supposedly there should have been a change, which, because of the nature of the substitution, does not manifest itself explicitly. So that is going to be from 0 to 1. So we will have 1/2 e to the first minus e to the 0. This is slightly simplified by e minus 1, since e to the 0 is 1. And let's go to our last problem, which is a polar coordinates problem. So we would like to compute the double integral over d of x squared plus y squared dA, where d is the disk of radius 2. Centered at the origin. So if we were to describe d in terms of polar coordinates, this would simply be all r and theta, so that r is between 0 and 2, and theta is between 0 and 2 pi. Of course, somebody might criticize having a less than or equal for 2 pi, since the points that have angle 0 are all, it's the same thing of saying that the polar angle is 0 or it's 2 pi. So it seems that we're taking some part twice, but it doesn't really matter, because that part doesn't correspond to anything that has positive volume or non-zero volume. So let's write now our integral. So we will have, let's start with dr, that will go from 0 to 2, then follow it with d theta, that will go from 0 to 2 pi. And now the integrand, well, we know that x squared plus y squared is r squared, right? So what we have is r squared squared, known as r to the fourth. And we shouldn't forget the Jacobian. And now it should be a pretty straightforward integration. I want the antiderivative of r to the fifth. That's r to the 6 over 6 from 0 to 2. And I want to take the integral of 0 to 2 pi theta. There's no theta, which means that all we will need to do is multiply by the constant function by the length of the interval, which is 2 pi. And what is that constant function? We take it from 2 to the 6 over 6. 2 to the 6 is 64 over 6. We can have a nice simplification here. And this should be 64 pi over 3. And that completes our problem. Thanks for watching.